Here we are, topic 10, our last machine elements lecture. Next time we'll talk about putting it all together, doing error budgeting and systems analysis. But we've covered couplings, structures, interfaces, actuators, all the stuff that goes into a machine, leaving what I think is one of the best for last, bearings. Bearings enable parts to move with respect to each other. And there's many different types of bearings for many different applications. You can never say one is better than the other. It depends what you're trying to do with it. Many types we can consider. In general, we'll group them into contact bearings, non-contact bearings. In discussing each of these different types of bearings, looking at issues like preload and mounting, in other words, how you use the bearings and how it affects the life and function of the bearing. Let's dive right into the beginning. Big things being made on a massive scale, pyramids. Some people once had thought that the blocks of stone were rolled in one log after another, and there's been some famous movies with time that have shown that. That seems to be called into question. Do they really have enough rollers, round enough, et cetera, to roll these stone blocks, or do they simply just slide them along on the ground? Famous people in the past, Leonardo da Vinci. John Harrison? Who is Harrison? He is the inventor of the world's first clock that would solve the longitude problem. Fantastic book to read about that, and how the bearings in the clock enabled accurate timing such that it allowed navigation to occur to reduce the number of shipwrecks. Heinrich Hertz, the man who did the theory of how points in contact with other objects, what kind of stresses and deflections they have, enabling the whole area of rolling element bearings to have some science brought to it that then enabled what was a fledgling industry to zoom, take off. Because once you have the engineering science behind the physical reality, it allows you to optimize. Henry Timken, who was the inventor of the tapered roller bearing, which revolutionized railroad industry. Why? Because before that, when you had just sliding contact bearings, the life of the wheels and axles wasn't so great and the loads were limited. But when you introduced rolling contact, you could have much heavier loads. There were ball bearings before Henry Timken, but ball bearings were limited in how much load they could take. But the roller bearing, which distributes the load over the length of a roller, enabled massive increase in load capacity. There have been other really brilliant people. Mr. Teramachi recently in the 50s and 60s helped to revolutionize rolling element linear bearings. Mr. Thomson, who invented the ball bushing bearing. There have been some modern heroes of rolling elements also. And those Kingsbury invented the tilting pad hydrodynamic bearing. Dozens of really brilliant people have allowed the industry to move forward to where it is today, and there's still a lot of work to be done. As a design person, your job is going to be to learn as much as you can about bearings and indeed all machine elements. You'll never stop learning. Always keep reading the trade rags, machine design, design news, medical products. There's no shortage of really excellent trade magazines that just reading the articles, looking at the pictures, clicking on websites, anything that starts to pique your interest, whether or not you need it now or not, build up this catalog of what exists in your brain. Whenever you can, go to a machine elements or a machine tool show. Go around, and the vendors will have all their products out for you to touch and feel. Touch is a very valuable element of how you start to build the catalog in your brain of what's available and what you can do with it. Talk to the application engineers. Ask them, well, what are some horror stories of how it works? Don't just tell me how wonderful it is. I want to know the limitations of it. Pack all that in your head and never stop doing that. The learning process is like bearings themselves. It should keep rolling on. So let's delve into sliding contact bearings, because they're the simplest bearing, which you see most often used. And a sliding contact bearing, in the simplest form, is just in a pin joint. just the interfaces between the pin and the joint is a sliding contact. It's rotary, but it's still sliding. So I will use, even though this doesn't fit, it's not the intended fit. If I have a round member of the joint and then the pin that goes through it, you can hear it. Sound is an indicator of what's happening. So it's smooth, but because of the sound, there is some wear. So I can only do this for a certain amount of time before the wear gets too big. That's not a bad thing. It's just you have to know what the limitations are. The key thing about sliding contact bearings is the coefficient of friction as a function of the velocity varies. There's something called the Strybeck curve, which gives us an indication of how the friction varies as a function of velocity. At lower velocities, the friction is much higher, and you have what's called boundary lubrication because you're actually getting mechanical contact between the bearing and the surface on which it rubs. Even though there's some lubrication in there, it's intermittent contact, and you have effectively a higher coefficient of friction. Once you get moving fast enough, you start building up a hydrodynamic layer, and you no longer have mechanical contact, and you'll see a sudden drop in friction. So on a shaft turning like this in the bore, that velocity, that surface velocity, may be a few meters per second when it starts picking up and you start running hydrodynamically. You keep running faster speeds and the apparent friction goes up, and what is happening is then you're shearing the fluid and now you're getting more hydrodynamic drag. How is that related to, quote, coefficient of friction in terms of that really should have nothing to do with the applied load? The applied load causing a classic Coulomb type friction really comes in more on the boundary layer. But remember, this just tells you then that you have a nonlinear friction effect, something to be aware of with all bearings. How in a sliding contact bearing can I start to assess what's appropriate to use? If I have metal on wood, how do I know what the coefficient of friction is? You can go online and say, what is the coefficient of friction in metal on wood? Well, it depends what kind of metal, what kind of wood, what the surface preparation is it greased or not? And remember, you can evaluate the coefficient of friction just by looking at the tilt. The tangent of the angle equals the coefficient of friction. And watch what happens when I have it at a static angle here. And let me take a different piece of wood. And watch this. So I'm at an angle here, and it just started to move. I can go to a slightly lower angle and get it moving, and it'll keep moving. See how I haven't changed it. That's the difference between dynamic and static coefficients of friction. Okay? Different materials will have different friction coefficients between themselves and other bodies. What makes a good bearing or a bad bearing is not necessarily the coefficient of friction, but the wear. So for example, aluminum on aluminum will tend to stick and gall and rip chunks of itself out of each other. In general, you want dissimilar materials. For rotary motion bearings that use a sliding contact bearing, a key is going to be on the efficiency of your machine. And recall from topic 5, we asked the question of, if you have a shaft and you put a wheel on it, for example, or a pulley, is there some diameter of the pulley versus the shaft diameter such that I can have very high efficiency of mechanical transmission of power even if I have a sliding contact bearing? because I may want to use a sliding contact bearing just because it's so cheap and can withstand very, very large loads. And indeed, when the wheel diameter to the bearing diameter, this is at 3, and here's at 5, depending on the coefficient of friction. So this green line is for a coefficient of friction of 0.1, which is very, very typical for example, steel on a polymer. At the bearing diameter of the wheel is 5 times the bearing diameter of the shaft. My coefficient of friction will vary from, this is about, or excuse me, the efficiency of the machine, or it looks like 96% to maybe 92 or 93%. This is St. Venet's principle in action, very, very often seen with sliding contact bearings. Look at all these different shapes of these modular sliding bearings that snap in you can get. Some with thrust faces, some without thrust faces, some with features that will hold them in the bore, like internal grooves. Again, there is no shortage of creative people out there who have faced the same types of design dilemmas you have over the decades, and the call for a solution to those design dilemmas have led to a wonderful plethora of different types of bearings you can get. So you must make sure that, particularly with bearings, you don't fall in the mode of, well, I can't find that, so I got to add this or add that or whatever. If you're just looking at one catalog, make sure you look at many different vendors to try to seek out who may have the bearing in the specialty shape you need that will reduce the number of features you have to design into your machine. For linear motion, if you go to an old style machine tool, for example, lathe, milling machine, you'll often see what are called a dovetail joint. A linear sliding bearing can be as simple as a flat part on a flat part. Let me get a different color here for the bearing. But that flat on flat has only stiffness vertically. You have to put other features and hence other sliding contact bearing surfaces to provide the guided motion you want. There are many different geometries with which to do that. I can have a bearing rail, and this is called a boxway structure, with bearing pads Here's a very good thought question for you in a minute. Why did I draw these lower guys real thin? These are called keeper plates. For a machine tool slide, if I have big giant loads up here, up top is lots, and why do I have these soft little keeper plates? These act as springs to keep this whole thing preloaded together, as we'll talk in a minute about the importance of preload in bearings. It also allows for locally, if the rail has a variation in height, if this keeper plate was really stiff, as I move the carriage, this is called the carriage, this is the bearing rail, along, come to a point where the bearing is too stiff and will not allow local deformations to occur. And remember, in bearings, this is absolutely critical, F equals Kx, but also your F horizontal, or excuse me, tangential, let's call it, equals your normal force times coefficient of friction. So you've got to be very careful that one, if your bearing is very stiff and you have a small motion deflecting the bearing, it can cause huge normal forces. In a rolling element bearing, you may not feel it because it's rolling element at such low friction. Oh, that's so nice. Oh, yeah. Whereas a sliding bearing, you'll know it very quickly. Oof. This K here you can control with the shape of the structure and how you preload it. This dovetail shape compared to this boxway shape, notice that for this carriage, I'm now going to have this type of bearing arrangement. And when I say a bearing pad, it's implicit in here that, okay, this is a separate, like a plastic element, but it doesn't have to be. It could be, for example, this is cast iron, and then there's either a steel carriage running on it, or it could be cast iron then with, it can be cast iron if it's well lubricated, or you could have plastic pads on it. Now, when we come into preload, again, you'll see that here, there's no way to really preload this arm well without the whole structure being a little too soft. And then that will be, what will be introduced is what's called a gib, or a tapered element. As the taper moves in and out, it closes and changes the gap. So with one gib here, you can preload this whole structure. Here, you would have to put in several gibs. Typically, you put in one here. This is a tapered carrot piece that moves in and out that will change this dimension and hence preload in this direction. And instead of using gibs on the bottom, you have these keeper plates that pull the whole thing down. When you look at construction sites, and you'll often see the scissor lifts going up and down. Notice how if I pin this joint here, that there's going to be a gap opening up. See how that gap opens up? You have to allow a linear motion bearing with that scissor lift. So you have pivots, and you'll still have to have a linear motion bearing to allow it to slide in. What kind of linear motion bearings do they use on scissor lifts that you'll see, for example, at construction sites? How do you design a bearing to last in a construction site? A rotary sliding contact bearing is relatively easy to make last with a rotary seal. But for the linear motion, how do you avoid dragging dirt in? Very important topics. One of the nice things about sliding contact bearings is they in general tend to be very tolerant of dirt. You can have a basic seal, and if dirt gets in, it'll cause a scratch just along where the dirt is, but the dirt won't get in and get rattled around and cause destruction everywhere. So sliding contact bearings, very, very low cost, can have good load capacity, very, very useful. Primary contact point issue is they're very stiff. Analysis issue to be focused on is what is the actual projected contact area for the bearing? Is it across the diameter of the shaft? And there's a certain length. Apply a force. And with a sliding contact bearing, I'm going to calculate the contact stress, force applied divided by diameter times length is the projected area. This contact stress has to be less than that which would cause mushment of the bearing, or yield of the material. And with a sliding contact bearing, no problem. Starts hot. Worrying about what is called, this is the sigma or pressure. Sliding contact bearings have a pressure times velocity limit. This is called the PV value. So you'll have to stay below a threshold, or maximum contact stress, and the contact stress you do apply times the velocity you apply will govern the wear of the bearing. That's all covered by the manufacturers in terms of what the wear that can be expected at different PV values, and what's the maximum PV value before you just burn up the bearing and melt it.